Okay, so in the last video we were reviewing the polar coordinate system, and now what we want to do is talk about functions and curves and things like that in polar coordinates. So typically in rectangular coordinates, when we're thinking about functions, more often than not we're thinking of y as a function of x. We've seen in this class that you can reverse that. You can think of x as a function of y also. But typically, we're doing it the other way around. In polar coordinates, most of the time, we're thinking of r as a function of theta. So you plug in different angles for theta and out pop different values for r. What we want to do here is look at a few different functions and kind of get used to the curves that we're graphing when we see those. Again, all of this is review from trigonometry, but it's stuff that people tend to forget about, so it's worth going over. First of all, the simplest type of function to consider in polar coordinates, or really any coordinate system, is constant functions. What happens if you take one of your variables and you set it equal to a constant? So for example, the function r equals c, where c is just some constant. Whenever one of your variables is missing from an equation, like the theta, for example, is missing here, we say that that variable is free to vary. What that means is when I'm plotting points for this curve, r equals c, I can plug in any value of theta that I want to, and the only thing that changes, or the only thing that really happens, is r is just equal to c for all of those values. So essentially what that does is it gives us the set of all points for which r is equal to that constant, which would just be a circle centered at the pole. Because if you think of what a circle is, for example, if this was r equals 2, it would give me the set of all points that are exactly 2 units away from the pole. But that is the same thing as the circle of radius 2, whose center is the pole. So that's what polar coordinates are really good at describing, circles centered at the origin, because it's so simply described here. What about if we have something of the form of theta equals some constant? So theta equals alpha, where alpha is a constant, for example. Well, that would represent the set of all points that form an angle of alpha with the polar axis. And the r is free to vary this time. So the distance from any one of those points to the origin doesn't really matter. It can be whatever distance we want it to be. But we just have to maintain that same angle. So here's an example. Theta equals 1. Remember, we're interpreting that 1 as 1 radian. Here, we have a bunch of points that these are in polar coordinates here. The r is changing, -2, -1, 1, 2, 3, but the theta is staying the same, 1, 1, 1, 1, 1, all of them are 1s. That would give me a line through the origin whose angle theta that it makes with the polar axis is 1 in this case, okay? What I want to do now is look at some more complicated functions. So in our first example, we're going to consider the curve r equals 2 cosine of theta. Okay, and I've already, on my printout, I've given the work here because the book gives this example, and I wanted to use this graphic. It looks a lot better than what I would have been able to draw by hand. But you can see that the graph ends up giving us this circle that is tangent to the pole right here and seems to be symmetric about the positive x-axis, or the polar axis. The way we would have graphed this, though, if we didn't have this already, is you have your function r equals 2 cosine of theta, and because theta is the independent variable, it's the input, I'm going to plug in a bunch of different values for theta, and then get the corresponding values for r, put them together to make these points. So if you think about it, if I plug theta in here, cosine or 0 in for theta, cosine of 0 is 1, 1 times 2 is 2. And then on to the next one, cosine of pi over 6, that would be root 3 over 2. Multiplying it by 2 gives me just a root 3 there. And then, you get all of these other values here. So the next step would be plotting all of those points in the plane here. It would be a lot easier to do this with one of those polar grids, which we saw on the previous video. So if you can imagine kind of concentric circles and spokes coming out and stuff like that. But these are the points corresponding to what we have in this table. So 2, 0 Remember, that's a distance of 2 away from the pole, angle of 0. Here we have an angle of pi over 6. This is pi over 6 right here. And this point would be root 3 units away from the pole, okay? And you plot a bunch of these out, and then you kind of connect them as you do with curves when you're first learning about graphing and rectangular coordinates. And we end up with this circle. Now, are we sure that it's a circle? Is there a way of saying, like, okay, it looks circular, but maybe that's just because of the way I drew it. Maybe it's more like an ellipse, or maybe it's, you know, there's imperfections in there that I'm not seeing in my sketch. How do we know for sure that this thing that looks like a circle actually is one? Well, there's a different way of approaching a graph like this. One thing we could do is try to take this polar equation and convert it into a rectangular equation using our conversion formulas. So there's a little bit of a trick we're going to use with this one. I'm going to multiply both sides of this by r. And what that gives me is r squared equals 2r cosine of theta. Now my reason for doing that is because r squared and r cosine of theta both show up in those conversion formulas. We know that r squared is equal to x squared plus y squared, and r cosine of theta is equal to x. So that multiplying it by 2 gives me 2x. Now we have the exact same equation, but in rectangular coordinates, which was a little more familiar to us. To see what this looks like graphically, I can subtract the 2x from both sides and then complete the square with those x's, which gives me this new equation right here. I'm letting you work out the steps in between. X minus 1 squared plus y squared equals 1. From algebra, we know that this is the equation for a circle whose center is 1, 0. Notice that that would be right here, right? And has a radius of 1. So does that match what we're seeing here? Well, yeah, the center would be on this positive x-axis halfway between 0 and 2, so that would be 1. And then the radius is definitely 1. I can see that visually right there. So this does match what we get when we convert this into polar rectangular coordinates. All right. Let's take a look at some more. Now, that was a graphing problem. There's different polar curves that we're going to look at, some of which are, a lot of which actually you don't tend to see in rectangular coordinates. You tend to only see them in polar coordinates. But before we get into those, there are some useful tests for symmetry that we can use when trying to graph these different curves. So for this one, if a polar equation is unchanged when theta is replaced by a negative theta, then the curve is symmetric about the polar axis. And this image here illustrates why. So you can see that this kind of pear-shaped curve here appears to have symmetry about the polar axis. And if you compare points, say for example r theta, if you replace that theta with a negative theta, then it takes that same angle but measures it clockwise from the polar axis instead of counterclockwise. That would take me to a point here that is vertically below this point here. So this point and this point are mirror images of each other or reflections of each other across the polar axis. Because this point coincides with this one when I reflect it, I have symmetry there. And I can see that that would happen with any other corresponding pair of points on this curve. So that's sort of your justification for that symmetry test. Replacing theta by negative theta leaves our polar equation unchanged. In other words, if I flip this entire thing about the polar axis, I get the same curve. Okay? Second one, if the equation is unchanged when r is replaced by negative r or when theta is replaced by theta plus pi, because remember, these two things accomplish the same goal. When you replace r with negative r, it's the same thing as rotating that point through an angle of pi. Then in this case, we say that the curve is symmetric about the pole. You can interpret this in two different ways. One is that you can think of this as the curve remains the same if you rotate it 180 degrees about the pole. Another way of thinking about it is if you take this curve and if you reflect it once across the horizontal axis and then again across the vertical axis, you get the same curve. But this is an example. So you can see here that this point if I call it r theta, the negative r theta is going to take that and swing it 180 degrees down to this point. So if replacing this r with a negative r lands me on another point on that curve, and if that happens for any point that I can choose on that curve, then I have this symmetry about the pole. Finally, if an equation is unchanged when theta is replaced by pi minus theta, then this curve is symmetric about the vertical line, theta equals pi over 2. That's the vertical axis here. And you can see from this picture why that is. If I do pi minus theta, then you can think of that as starting from an angle of pi and subtracting a theta from it. So that's like, if this is theta right here, then this right here I could think of as theta as well. And so what I get is like this isosceles triangle of sorts. So if r theta is a point on my curve over here, then using that little transformation on it, changing theta to pi over theta, basically is like a horizontal reflection. It takes me from here over to here, and if it lands me on another point on that curve, then I have symmetry there, okay? So those are symmetry tests. We're going to use that here. I want to test the equation r equals cosine of 2 theta for symmetry, and then I want to graph this function. So looking at our tests, the first thing I can do is replace theta by negative theta. So if I did that, r equals 4 cosine of 2 times negative theta. Okay, now here's where you have to know something about the cosine function. This is the same thing as negative 2 theta, but that would be the same thing as 4 cosine of just 2 theta. The negative goes away, and the reason that happens is because we know that cosine is an even function, and that's a property of even functions. So what this means is that we have symmetry about the polar axis. Symmetry about polar axis. So whenever I graph my function here, I can take it and reflect it across the horizontal axis to get a mirror image on the other side of that axis there. Okay. If the equation is unchanged when r is replaced by negative r, or when theta is replaced by theta plus pi, then the curve is symmetric about the pole. Okay. Now, I can choose either one of those, but let's say that I do, let's replace this with theta plus pi. Let's try that one. If I say r is equal to 4 times cosine of 2 times theta plus pi. Okay, well, that's the same thing as 4 cosine of 2 theta plus 2 pi, right? However, we know that if we're taking the cosine of an angle, and then if we add 2 pi to that angle, and then what that does is it just rotates that angle a full circle and brings me right back to the starting point. So the cosine would still give me the same value. This would still be 4 cosine of 2 theta. So now I have symmetry about the pole. Okay? Let's test for the last type of symmetry. So for the last type of symmetry, what we do is we replace theta by theta minus 2. And if we get the same equation after doing that, I should have something that's symmetric about the vertical line, theta equals pi over 2, so the vertical axis. So let's do that. R is equal to 4 cosine of 2, and we're replacing theta by pi minus theta, like that, okay? All right, this is equal to 4 times cosine of 2 pi minus 2 theta. But again, another way of writing this is 4 cosine of negative 2 theta plus 2 pi. I can rearrange those. And then I can think of this as taking the angle negative 2 theta and then just rotating that through another full circle, another 2 pi, taking me right back to my starting point. So this is equal to 4 times cosine of negative 2 theta, as if I never did another full circle. And then that negative, we already know because cosine is an even function, it gets eaten up by that cosine, and I get this, which is the same function that we started with, which means I also have symmetry about theta equals pi over 2. Now this is really useful. We have all three types of symmetry here. And the reason this is nice is because it restricts the amount of things I have to plug in for theta to get a picture of what this graph looks like. So here's what I'm going to do. We're going to plug in some values for theta and some values for r. Okay. We're going to plug in a 0. What else should we plug in? Let's plug in maybe pi over 6, pi over 4, pi over 3, and pi over 2. And then, in fact, that's actually where I'm going to stop. Okay. Let's see what values we get when we do that. So, all right, 0. If I plug that in, 4 times cosine of 2 pi. So I'm doubling the 0, which is still 0. Cosine of 0 is 1 times 4. That would just be a 4 right there. Okay. And here I'm going to write r equals 4 cosine of 2 theta here for reference, because I can see that it's off the screen where the function is off the screen up there. If I plug a pi over 6 in, I double it, so I get pi over 3. Cosine of pi over 3 would be 1/2 times 4. That would be 2. So that's fine. Cosine of, if I plug a pi over 4 in, that gives me cosine of 2 times that. Cosine of, if I double pi over 4, I'm going to get pi over 2. Cosine of pi over 2 is 0, so this becomes 0. Okay. Now, next up, pi over 3. So I double it first, and I get cosine of 2 pi over 3. That puts me in the second quadrant over there. Here's 2 pi over 3. And what is cosine of 2 pi over 3? Well, cosine of 2 pi over 3 would be negative 1/2. And negative 1/2, when I multiply it by 4, would give me negative 2. Finally, plugging a pi over 2 in, doubling it gives me pi. Cosine of pi is negative 1 times 4 would be negative 4. All right, now let's take a look at how to graph these values in our polar grid. So first of all, when theta equals 0, which puts me on the polar axis, r is equal to 4. So 1, 2, 3, 4. I have a point right there. Pi over 6, which is here, I get r equals 2. So 1, 2. That would put me right there. When I get to pi over 4, here I end up at the pole. Okay? So here's what I'm seeing. I get this. I'm not drawing it very well, but I get something kind of like this, right? Now, I could actually probably skip the rest of the work, but I'm not going to do that. Well, no, actually, I can't skip it yet. I still do have some more to do. Pi over 3. Where is pi over 3? Pi over 3 is right here, right? So if I plug pi over 3 in, I get a negative 2. So that means that I go through a 180-degree angle, and now I'm going in the direction of 4 pi over 3, and I go 2 units in that direction. 1, 2, like this. And then pi over 2, if I plug in a pi over 2, I get negative 4. Well, pi over 2 is here, but the negative value for r reflects this down, and now I go 4 units down instead of up. 1, 2, 3, 4, like this. So now this curve goes like this. Okay? Now it turns out that's enough to get a graph of the whole thing, because I could keep plugging in different values of theta, but because I did these symmetry tests, I know some things about the symmetry here. So first of all, we have symmetry about the polar axis, right? So the polar axis is this horizontal axis right here. So if I were to take this guy and reflect it across the polar axis, I would get this point reflecting down to, what was that, pi over 6? I would get this guy reflecting down to here, and I would get kind of a matching curve below that horizontal axis right there. So I get something kind of like that. But then this curve down here would reflect above the polar axis. So this point is going to reflect up to this point, right? And then this point is going to reflect up here, 1, 2, 3, 4. I'm going to get this. And so I'll get kind of a reflection of this curve, but up here now. It's going to go like that. Okay. What else can we say? Well, I have a reflection across, or symmetry across theta equals pi over 2 as well. Remember, that's the vertical axis. So now all of this stuff can be reflected across my vertical axis. So this little leaf right here can be reflected this way. And so I'm going to get a point that corresponds to this guy right there. 1, 2, 3, 4. I'm going to get one right there. And then one down here. What is that? That's 7 pi over 6. 1, 2, like this. So these guys are reflections. And I get something that looks like this. Right? And then when these two curves reflect across this way, across my vertical axis, I can get these points and put those together. And then I get this rose shape. In fact, that's what we call this curve. It's a rose. It's a rose with 4 petals, actually. Now, it took me a while to do that because I was talking through it, but the symmetry tests that I did here helped me to figure out ways of reflecting these points in such a way that takes some of the work out of it, because I didn't have to plug in a whole bunch of theta values, just a handful of them. Okay, symmetry about the pole, we didn't end up using that symmetry test, but you can see that symmetry here. So notice if I were to rotate this whole curve 180 degrees, I would have the same rose there. Okay, so we could do a ton of problems like this. We do that in trigonometry, where we graph a bunch of these things and kind of classify these different polar graphs. But because you cover that in trig, we're not going to spend any more time on that. Instead, I'm just going to catalog them here. So what we have here is a table of different curves. We've looked at this. R equals a constant, gives me a circle whose radius is that constant, A in this case, and whose center is the origin or the pole. If you have R equals a sine of theta, then what we have is a circle that's tangent to the pole and is symmetric about the vertical axis, the line theta equals pi over 2. This circle can appear below the x-axis as well, below that polar axis. And the way we know which of these two cases we're looking at is whether A is positive or negative. If A is positive, then our circle will be above the x-axis. If it's negative, it will be below it, or the polar axis. Okay, so not only that, A tells me the diameter. Yes, the diameter, not the radius. It tells me the diameter of that circle. We already saw that in our previous example. If you have a cosine of theta, similar thing occurs, but now we have a circle that's still tangent to the pole, but symmetric about the polar axis. You can use your symmetry tests on these guys to see that happening. This one, R equals A times theta, gives me a spiral. And that kind of makes sense. As theta gets larger, we wind our way around the pole. But assuming A is like a positive number, for example, if theta gets bigger, then R will get bigger. So the more we wind around the pole, the further away we're getting from it. And that creates a spiral. This next class of curves are what we call limacons. Notice the C has this little tail there, so it's limacons is how we pronounce that. These always come from equations of the form R equals A plus or minus B sine of theta, or R equals A plus or minus B cosine of theta, and here we're assuming that both A and B are positive numbers. There's a little note here that says orientation depends on the function sine or cosine and the sign of B, the coefficient. It's very similar to this. But here we have the 4 different types of limacons that can occur. We have these guys, which are called inner loop limacons. We have cardioids. Cardioid, if you think of the word cardiac, it's like from the word heart. And that's kind of what a cardioid resembles, somewhat like a heart shape. It's got this cusp right here. That little vertex of that cusp is always at the pole specifically. And then we have these things called dimpled limesons. Dimpled limesons look similar to cardioids, but that little point there has pulled away from the pole and is more of a smooth curve instead of a cusp like that. And then we have convex limesons. This thing looks like a circle, but it's not a circle. It's basically like this dimpled limeson if you kind of pushed the dimple out, and it's not perfectly round. It's just not concave anywhere. Okay, so we use the word convex for that. These conditions tell us how to determine which of these we're looking at when we're given an equation in polar form. So again, if you have r equals a plus or minus b sine of theta, if a is less than b, so the number being added here is less than the coefficient, and remember these are always assumed to be positive, then you get an inner loop limeson. If they're equal to each other, so if I have something like 4 plus 4 sine of theta, you would have a cardioid. If a is greater than b, that's where you get this dimpled limeson. And then if a is greater than or equal to 2b, that's where this thing becomes convex. Okay? And then the sine of the cosine and the sine of your b here tells me the orientation. So all of these would be of the form r equals a plus b sine of theta, because b would be positive, and I'm using a sign that orients this upwards. If the b was negative, these would be oriented downward. If I had a cosine, it would be oriented either to the right or to the left, depending on whether b is positive or negative. So all of that stuff we take into consideration for these. Next up, we have roses. We just graphed one of these. Our rose looked similar to this one, where it had 4 petals, or a 4-leaved rose is what they call that here. And notice the form of the equation. It's similar to what we had. We had r equals 4 cosine of 2 theta. But generally speaking, we could have r equals a cosine of 2 theta, and that a will determine how far from the pole these leaves reach. In our example, we went 4 units out to the tip of each rose. Okay? If I have r equals a cosine of 3 theta instead of 2 theta, I end up with a 3-leaved rose. And we can keep doing this, a cosine of 4 theta, a cosine of 5 theta. The pattern you may notice, which is mentioned here, is that if I just call it a sine of n theta, or r equals a cosine of n theta here, then whether n is even or odd comes into play when we're determining how many leaves these things have. So if n is an odd number, then that is exactly how many leaves it'll have. Notice cosine of 3 theta had 3 leaves. Cosine of 5 theta, 5 leaves. If n is an even number, we get double that number of leaves. So for a cosine of 4 theta, it's 8 leaves, not 4. Okay? And then you'll notice where some of the symmetry occurs. Like this 4-leaved rose here had all 3 types of symmetry, but this guy does not. This guy has symmetry about the polar axis, but it does not have the other 2 types of symmetry. So that all of that stuff, you can kind of determine why it's working out, why it's not working out the way you expect it to using those symmetry tests. The last type of polar curve is this guy. We call these lemniscates. They look like figure 8s, and they can either be symmetric about your polar axis and theta equals pi over 2, or they can be symmetric about the origin, which is what this guy is. These are the equations that give us those. Notice that r is not isolated anymore. It's r squared equals a squared sine of 2 theta, or r squared equals a squared cosine of 2 theta. Those will give you those lemniscates. We graph some of these by hand, but in 10.4, when we're using these polar curves and doing calculus with them, I'm not going to go through the trouble of graphing anything by plugging points in. I'm going to use some conventions that we have, or technology. If you go into something like Desmos, which is a great online graphing calculator, it's free. Desmos knows how to handle polar curves. If you start typing r's and thetas into your equations, it'll graph them in polar form. So that's something that's worth messing around with as well. All right, that's going to wrap up 10.3.